Up until now, we have talked about the magnetic field around a wire. We've also talked about magnetic forces that are exerted on a wire that has a current passing through a separate magnetic field. So we've kind of played around with the magnetic field around a wire. However, up till now, we haven't yet calculated the magnetic field around a long straight wire. And we can do that now. When you take a current through a wire, we can actually calculate its magnetic field, and we find that it's inversely proportional to the distance from the wire. The way we calculate that is indicated by this equation here, mu naught times the current I divided by 2 pi r. Mu naught is a constant that we call the permeability of free space. It has a value of 4 pi times 10 to the minus 7th Tesla meters per amp. And so whatever your distance is from your wire, so if you want to measure the magnetic field here, that's your distance r right there. Yeah, it's a pretty simple equation. And of course the direction, we've already talked about how to find the direction of a magnetic field around a wire using the first right-hand rule. Now this is interesting. We can actually combine both of the topics that we've talked about so far. We have a current which generates a magnetic field, and we have another current passing through that magnetic field. Let me explain. So you have two wires, wire 1 and wire 2. And they're some distance d apart. And current I1 is going to generate a magnetic field that goes around wire 1. Well, wire 2 is close by, which means that wire 2 is now passing through the magnetic field for wire 1. So the magnetic field generated by wire 1, we use this equation, mu naught over 2 pi times I over r. But we want specifically what is the value of the magnetic field at wire 2. So that's r would be a distance d. So we just use d for our radius r. Okay, and then we take that and we plug that into the magnetic force on wire 2 would then be current 2 times the length of the wire times the magnetic field which is generated by current 1. Well, if you substitute this in, then your result is this equation down here. That the force on wire 2 is going to be mu naught over 2 pi times the product of the two currents divided by the distance between them, all of that times the length of the wire. So, in other words, sorry, I lost my words there. The magnetic field generated by current 1 is going to exert a magnetic force on current 2. Well, what direction is that magnetic force? We just found the equation to find the magnitude, but how do we find the direction? Well, remember the right-hand rule. Take your right-hand fingers, point them in the direction of your current, which in this case is up, and your magnetic field, which is going counterclockwise here. At this point, your magnetic field is going into the board, so point your fingers in the direction of I, up. Curl them so that your magnetic field is your fingers point in the direction of the magnetic field into the board. That means that your finger, or your thumb, generates a force that's going to the left. Well, here's an interesting thing. Oh, sorry, let me finish that thought. Basically what that would do is that would pull I2, pull that wire so that the wire would actually bend inwards, like so. It would bend the wire in. Now here's the interesting thing. Current through wire 2, so I2, is also generating a magnetic field that is having a very similar effect on I1. So the current around I1 generates a magnetic field around, that goes through B1, that goes through I2, and I2 generates a magnetic field, B2, that goes through I1. And as a result, they're exerting a force on each other, and you would actually see these currents, or these two wires, bend inward towards each other. What if you have two wires that are flowing in opposite directions? Well, that reverses the direction of the force, and they would end up bending outwards, repelling each other. Okay, that's the magnetic field in a wire. Now let's talk for a second about a solenoid. A solenoid is just a long wire that is wrapped in coils, like so. Picture does better than I can, so I'll just leave it like that. Now, remember early on in the first video, we talked about one loop of wire. If you have a current in that loop of wire, you can use the right-hand rule, and you see a magnetic field passing through the wire, and it looks something very similar to this picture right here. That was a good introduction to solenoids. Well, if you have current here, following the right-hand rule, you see that the magnetic field is always pointing to the right for each of these loops. How strong is the magnetic field? It turns out that the magnetic field is going to be equal to mu naught, the permeability of free space we saw a couple slides ago, times N, the number of coils in the wire, times I, the current within the wire, divided by L, where L is the length of the solenoid. Well, solenoids are fun. They're great. But what good are they? Well, let me show you, demonstrate a couple things that you can do with them. If you have another magnet and you place it right here so that the South Pole is right there and the North Pole is right there, what's going to happen? Well, the South is going to repel the South, and this South on this end is going to be attracted to the North. So it's going to actually take that bar magnet and pull it inward towards the center of the solenoid. Well, what if I take my magnet and I flip it around so that I have South here and North here? Well, then North will repel North and South will repel South. That'll shoot this magnet out of the solenoid. Okay, what good is that? Well, we can use this principle of solenoids in a very simple device. Let's say that we have here a simple bar magnet that's attached to a spring. We'll say we've got South on that end, North on this end. And we have a solenoid that's connected to a voltage source and a switch. When the switch is closed, let's say that it forms a North pole on this side and a South pole on this side, which we saw would then take the magnet and pull it in. And when it would do that, then theoretically this bar would be going fast enough that it would have momentum and hit a bell, ring the bell. Well, if you wire this setup just right so that this bell is somewhere in the middle of your house and the wire comes out outside of your front door so that the switch is just outside of your front door, then you have someone push a switch known as a doorbell and it rings a bell inside of your house. This is how many old-style doorbells work. Today we have more of a digital system, but this is just a really fun demonstration of how you can use solenoids. Solenoids are used in many cases. Factories that construct things, you're going to have lots of solenoids. I'm quite sure that phone factories that build your phones use solenoids in their production, um, in making the motherboards and the memory chips and everything like that. Your car is going to use solenoids. Solenoids are used in a lot of more complicated electronic machinery.